So yeah, a truly sparse and general implementation of gradient-based synaptic plasticity. What the hell does that even mean? It basically means we made EPROP and these types of learning rules a little bit faster by using some cool techniques from automatic differentiation. And yeah, thanks for the opportunity for being able to present this here. This is actually a talk that is not very well suited to be presented. It's much better to read the paper because you need some time to figure out the math. At least I did when I made the work. So the people that helped, the other guys, Anil and Florian, are also here. There's two of my master's students, and big shout out to them. The project wouldn't have been in existence without them, and they're great people. You should absolutely talk to them. So yeah, and the third guy, I think all of you know, Emre. So this is Emre's first contribution. I just stole this slide from him, from his talk, so you're already familiar with that. I think one of the biggest achievements for me as a PhD student is that if the PI makes the slide for you, you have actually really made it. So the idea here is you have long-term potentiation, right? The synapses change their weights, and that usually happens when you have an action potential and a postsynaptic potential, and they have a very strong correlation, and that's when you change your weight, and then the magnitude of the weight change is usually proportional to some higher level information like reward or an error or something. And you can actually translate this, or you can not translate it, but connect it to gradients and learning with loss functions and computing gradients and so on. This is all the stuff that Emre already presented, right? You can get these three factors, especially when you're looking at spiking neurons, and your weight change is basically proportional to your gradient in the system. And gradients is what we are actually interested, because gradients is what actually really works, right? Like in practice, whenever you want to solve a real-world task, you will have to use gradients. We are sadly not at the point yet where we can use other techniques. So typically when you compute gradients, you would do this with BPTT in a general setting, but in biology, in neuromorphic computing, we are also interested in having other biological constraints. So typically you will have to adjust these BPTT rules a little bit. And one very popular choice is EPROP. Don't be scared by all them. I know it has 3 indices, very scary object. The key importance here is for EPROP, the central equation is this equation. And the central thing about this central equation is that it's a recurrence relation. So it has this like t here and t minus 1 something. So there's a temporal correlation. And this is what we made cooler. So we will come back to this, and it will look much less scary then. But just, you know, this is the object we will look at throughout this talk. So yeah, this recurrence relation. And the cool thing about EPROP is it's online. It can do online learning, and it can be implemented very efficiently. It can also be implemented locally and so on. But let's be honest, in practice, nobody does that, right? What typically people do is, if you train, for example, stuff with SNN torch and so on, and you want to have your EPROP rule, what you do is you use BPTT like you usually do. So you do a loss function dot backward, and you do a stop gradient somewhere. Then mathematically, things are equivalent. I don't want to show that here, but it's true. And then you have all the negatives of BPTT, right? It's not online anymore. You have a forward and a backward pass. It's very memory intensive, so you can't train for a very long time horizon. And the other thing that you can do, which they did in the original paper, is they implemented stuff by hand. But implementing stuff by hand scales really badly in terms of manpower and so on. So you can make mistakes when you derive the gradients and so on. If you want to test out a new neuron type or whatever, that also scales really badly. So, and we removed all these things, sorry. We removed all these things, and we have the best of both worlds, so to say. So how do we do that? So typically when you compute gradients in the machine learning domain, what you use is automatic differentiation. And this is something that is like a very, let's say, obscure thing. Most people don't think about this really well. For them, it's just like the loss dot backward, and that's your only contact with autodiff usually. So what is autodiff actually? Autodiff is a way to compute derivatives algorithmically up to machine precision. So it differs in that way from like these finite differencing methods, where you also get an error due to approximation. You don't have this approximation error in automatic differentiation. And I'll show you how this works. So before we go into that, autodiff is not only a machine learning exclusive tool, it's also used a lot in robotics, computational fluid dynamics, and so on. So it's a very broad field, and a lot of people use it actually. And the other important thing is, your main contact point with autodiff is dot backward in torch usually. Many people equate those two things, but autodiff is actually not the same as backpropagation. Backpropagation is a particular algorithm for solving a task. It's similar to, like, for example, having sorting. where your algorithm is a bubble sort. So basically, backpropagation is the equivalent of a bubble sort in that case. It's a particular type of algorithm. And there's many, many more algorithms, and you will going to dive into that a little bit. And these other algorithms, they actually have a lot of other benefits. So for automatic differentiation, there's only 2 ingredients that you need to make the thing work. The first one is the chain rule. In a single variable case, the chain rule is just the multiplication of the 2 derivatives of the chain functions. And in the multivariable case, you just multiply the 2 Jacobians with each other. Keep that in mind. That is important throughout the talk. The other thing that you need is you need elemental derivatives. So what you need is somewhere in the code, when you go into PyTorch, when you go into JAX, when you go into TensorFlow, at some point, there's a big ass file. There's a file that has like 10,000 lines, even more, where one very poor intern had to take all the time to implement the derivatives of all the functions, of all the elemental functions. So for example, if you have like a sine function here, at some point he implemented this, okay, for a sine, the derivative is a cosine. For a cosine, the derivative is negative of the sine. For tangents, the negative, and so on, you know? And you have that there. And these are called like elemental derivatives, and the corresponding functions are called the elemental functions. And these things you always have, and these things, together with the chain rule, you use to assemble your new program that computes the derivative of the program that you gave it. So how does this work? So I'm not going to talk about backprop here. I'm going to take a different view, a view that is not very well known, but that can be very helpful for automatic differentiation, which is called the graph view. The graph view on AutoDiff has the advantage that it allows you the systematic construction of AutoDiff algorithms. And it also allows you to tailor AutoDiff algorithms to functions so that you can, like, for example, save on resources like memory, compute, and so on. And so how this works is the first step that you always have to take is you write down a function like this f here. And then, you know, we have this big library of elemental functions. So the first thing we should do is probably like decompose it into these elemental functions, which is what we do here. This object here is called a tape. It's going to come up throughout the talk again and again. And what a tape is basically, you can think of it like some sort of pseudocode. So in a sense, it's in practice, this will be written in C or Python or whatever. And there we record everything that we do to construct our algorithm. And so clearly, when we have the graph view on automatic differentiation, what we want is we want a graph somewhere. So typically here, what we use is the computational graph. The computational graph is nothing else than representing the data dependence between the different operations in the in your function that you just typed out. So this is like you have the tape, and then you have the graph. And the important thing is the graph doesn't really exist in the sense that this is not what you run in the end. This is more like kind of a mental bookkeeping device to construct your algorithm. And what really matters is the stuff that we write down the tape, because remember, the tape is the program that we will actually execute later on. So the other thing we need, right? So far, we only had a graph and we had the data dependencies, but of course, when you want to compute derivatives, you should also have them somewhere. So what we will do is something that will seem very ad hoc now in the beginning, which is we add derivatives to the system by attaching them to the edges of our graph. In particular, what we do is for every edge that we have here, what we attach is we attach the derivative of the destination vertex with respect to the source vertex. For example, for this edge here, that goes from -1 to 1, we attach the derivative dv-1 at dv1 after dv-1. So we do that. In this case, v1 is v-1 times v0, as we see in the tape. Partial derivative rule, we arrive at just v0 in this case. Can get a lot more complicated. And then we populate the entire graph with all these derivatives, and we store we save all of them to the tape. That's important because, you know, they contain the derivative information. And now we have implemented the first part. If you remember, for AutoDiff, there's 2 things that you need. The first one is the elemental derivatives, and the second one is, of course, you need the chain rule. You need to be able to assemble all of these into an algorithm. And this is what we are going to do now. So we introduce a rule, which is called the vertex elimination rule. So what happens in the vertex elimination rule is we say, okay, when we eliminate this vertex v2 here, what we do is we take all ingoing edges and multiply their results with the respective with all of the outgoing edges. So in this case, we multiply this guy with this guy and this guy with this guy. And when we do that, we create a new edge, this one here, and we add the product of those two things to the edge. And then we delete what remains. And we, of course, again, save this multiplication to the tape. So what do we do in the other case down here, right? Here, you already have an edge there. That's not good. So what we do in this case is we add the results. So we multiply these two guys together, and then we add it to what already exists, and then we move it to the tape as well. This seems very odd in the beginning, but in the end, if you look at it, it's just all of the rules that you should know from mathematics. This is just applying the chain rule, right? If you think of like of this chaining of like the operation that happens at V2 and V3, right? You just multiply the derivative of the one guy and the derivative of the other guy. It's just literally just the chain rule. And also here, where we had this additional edge means basically that you have an implicit and an explicit dependence, and then we just apply the rule of total derivatives. So we have to add these two things together. Okay. So we're not done yet because there's another vertex. There's V1, and we have to eliminate V1 as well. So we do that. We apply the same stuff as before. So we take those two things, we multiply them together, save them to the tape. Do that for the other guys, multiply them together, save them to the tape. Then we take these two, multiply them together, save them to the tape. And finally, for the last one, we do that as well. Come on, go away. And yeah, and then we have eliminated, deleted all the edges, and we can eliminate the vertex. And now what we see is there's no more vertices left where it makes sense to eliminate, right? We only have these output and these input vertices, but there it wouldn't make sense to eliminate them because you either have no incoming or no outgoing vertices. So we're kind of done now. And the cool thing is, this kind of looks a little bit odd, but in the end, what you can prove mathematically that every edge now that in this bipartite graph contains an entry of your final Jacobian. So if you apply this thing, you can literally construct an algorithm, which is all the stuff that we stored in the tape. And out you get the formula for a Jacobian. And then I think there's like two immediate questions that arise here. First of all, how do you choose like what you actually do? Like why did you start with vertex V2 and not with V1 and so on? And the cool thing is, if you do it in the order V2 and then V1, and if you look at the mathematics, the thing that falls out in the end is the same formula as backpropagation. And vice versa, in this case, if we would have started with V1 and then V2, the thing that falls out in the end is the same as forward mode AD. So there's a direct connection between the graph view and these typical backpropagation formulas that we have. And for the people that know autodiff a little bit better, they also should know that forward mode is computationally more expensive than reverse mode. And this is also true in this case. So for this algorithm, if we do the elimination order 2, then 1, you have 6 multiplications and 1 addition. And if you do it the other way around, so if you do 1 and then 2, you get actually 8 multiplications and 2 additions. So there is a difference between the elimination orders in terms of the computational requirements that they have. And you can actually generalize this for every elimination order that exists, right? For larger graphs, you obviously have more complicated elimination orders. They all have different computational cost. And the question is now, okay, which one is the most efficient one? And the cool thing is, you can actually tailor your computational, your autodiff algorithm to your computational graph to make it the most efficient. And this was, for a long time, not an unsolved problem, actually. And so we did this, Emre and me, and we got like a new spotlight paper for it, where we use reinforcement learning to actually find these optimal elimination orders. And it works also end-to-end. So what you do is you just write your function in Python, gets translated into this computational graph. We take this computational graph and use the vertex elimination rule as some kind of an action space, basically. And as a reward, we use the computational cost. And then we throw like a reinforcement learning algorithm, like, for example, AlphaZero or PPO at it. Out comes an elimination order. And this elimination order then gets translated using a compiler that we wrote into the optimized autodiff algorithm. And this works very well in practice. So here you see, first of all, the convergence curves. The reinforcement learning algorithm completely outperforms like the state of the art. Also on many, many different tasks. And we also wrote this compiler for Autodiff that also translates these elimination orders in actual real executable programs that are JIT compilable and all of that. And again, like this is the green curve that you see here. Again, it's also much, much faster than everything that currently exists and is out there. So, and if you look here at these results, we also investigated stuff like MLPs, transformers. It doesn't work too well because Backprop is already a very good algorithm for these things, so there's not much that you can gain. The interesting question is though, okay, a transformer, what the hell? This is like a big ass object, has like millions of parameters, billions of operations. Are you telling me that you ran the reinforcement learning algorithm on this big thing? And no, we of course did not. This would be infeasible. What we did is we kind of did another invention that was necessary, which is called like a tensorized vertex elimination. So let's take the simple example here, which is just like a linear transformation with a nonlinear function. And in this case, we allowed the vertices not to be scalars only, but to be lifted to be also matrices, vectors, and so on. But when you do that, the derivatives that you assign to the edges, they have to be Jacobians now in their own right. And you're no longer multiplying things, but you instead are doing matrix multiplication, or even worse, tensor contractions of these Jacobians. And many of these Jacobians, they actually have like a static sparsity structure. So they have a lot of like off-diagonal zeros and so on. And it becomes computationally very infeasible if you just carry all these zeros along. So what we did is we implemented like a sparse version of it that replaces these contractions of a lot of zeros with just very fast element-wise multiplications. And you can see this here, right? This is like a three-dimensional tensor, but it has only like values on the diagonal. This is this like weird cube here, and like only the dense parts that are actually non-zero. The same goes for this Kronecker delta here, right? It only has values on the diagonal. So if you would contract these two guys with each other, you have a lot of zeros that you multiply, but you can just instead multiply the diagonals together, and that's what this guy is doing. And this is also this compiler that we wrote. Is GraphX. This doesn't exist, by the way, so I was the first person who actually implemented something like that. It was terrible. But this way, you can actually make all of this work at scale very, very fast. So you can actually apply this, for example, also to a simple live neuron. And you see actually a simple live neuron has a lot of sparse components in there, a lot of sparse Jacobians and so on. And we can apply then elimination rules to this guy as well. And arrive at a derivative for this, for this live neuron. The interesting thing though now, or at least until now, we only were talking about the spatial part here, right? But if you have spiky neurons, you're not only interested in spatial derivatives, but also into temporal derivatives. So the last thing that I want to talk about is like temporal credit assignment. So how to combine what the stuff that I just presented with like actually doing stuff in time. So if we look at this recurrent neural network here, so the first thing you always do with a recurrent neural network is you unroll it in time, because then only then it's somehow tractable from a reasoning perspective. And if we compute derivatives of this guy, of this unrolled thing, usually what you do is you get this DL after d theta, and this is just a sum over many different derivatives. And typically what you want is you want DL with respect to DH. But there's like, it's not straightforward to compute this. You have to take some things into account, because there's like multiple paths basically that lead to this H of T, right? And all of these multiple paths, they have different values. So they have different derivatives attached. And what we know now from this vertex elimination rule is if you have multiple paths, right, you have to add them up. And that's what you need to do. So this DL after DHT is like a sum of multiple components. And you can rearrange this sum, and you can rearrange it further. And in the end, what it will turn out is that this DL after DHT is nothing else. It can be computed very efficiently with a recursion relation. And if you look at this recursion relation, this is like the recursion relation of BPTT. You can see that also here, it's a recursion relation that walks backward in time. So it starts at t+1, but it goes to t. So this is this forward-backward pass thing that I was talking about earlier. And you also see that this is quite different to EPROP. EPROP walks forward in time. The big disadvantage of this going back in time thing is that you have to store all the intermediate states in the forward pass. This is why BPTT has a linear scaling in time, which makes it very inefficient and which also is what's typically keeping you from training very long horizon SNNs. But there's another way we can do this. We can look at this computational graph again, and instead of like basically accumulating our derivatives above this like horizontal line here, this line of causality, we can also go below. And instead of looking at DL after D theta, we can, DL after DHT, we can also look after DHT after D theta. And then again, we have 3 different paths that lead there. And they all have their own values again. And because we have different paths, again, we need to sum all of these. We can rearrange them again. And again, we get a recursion relation. But this time it's a recursion relation that walks forward in time. And because it walks forward in time, it's much more memory efficient because you don't have to store all the stuff. So it's suddenly something that is constant in time. But if you look at the compute scaling, it's terrible, actually. It scales with n to the 4, where n is like the number of neurons or something. So it's much more compute inefficient. And that's also, so this guy is called RTRL, by the way. So that's the reason why you don't train with RTRL, because it would take forever. It would be super memory efficient, but it just takes forever to compute it. So that's why you never use this in practice. And now the interesting question is, can we actually have the best of both worlds? Can we have BPTT and RTRL somehow? Can we have the memory efficiency of RTRL, but the compute efficiency of BPTT? Can we get the online learning and so on? And actually, yes, we can to some degree, if we do some approximations. And this is exactly what EPROP does. So the thing we need to do, the core interesting quantity is this H of t. H of t is basically like the causal dependence of the state onto itself in the past. So it's dH of t after dH of t minus 1. And if we look at this, and we, for example, assume that we have like a simple live neuron, this guy like factorizes kind of into these 2 components, into like an explicit and an implicit recurrence. And EPROP, in the end, what it does is it does nothing else than neglect explicit recurrence. And if you do that, you get very lucky, because what happens is your H of t becomes a diagonal tensor now. And remember early on, I was talking about how we are very good at doing diagonal stuff. And this is exactly what happens here. So H of t becomes diagonal. And because H of t and also F of t are diagonal, the G of t, because of the recursion relation, also stays diagonal. So everything's diagonal all the time. So we can apply this graphics tool that I wrote and just replace these diagonal multiplications with very efficient element-wise multiplications. And the new algorithm we arrive at, or the new tool that we arrive at, now has like a very efficient compute scaling and a constant memory scaling. That's cool, because now we have the best of both worlds, right? So how does this work in practice? So if we see our method in action, right, we look at this plot above there. So the green line is naive EPROP. So if you would like implement it basically by hand, that doesn't scale well. Then we see like BPTT has a linear memory scaling as you would expect. And then this is our method. And you see like you can basically, the number of times this can grow arbitrarily large. It still works. This is for like a neural network at scale. And I think Anil even tried out like 20,000 steps. It probably goes up to 100,000 steps. So you can just now train a neural network to 100,000, spike neural network to 100,000 steps with this guy, which is, I think, kind of cool. And same you see in the graph below there, right? Like the peak memory usage of this algorithm with the number of hidden neurons is just so much more favorable compared to everything else that we have. The same is actually true for compute. So even from a compute perspective, this guy is a lot faster than the other guy, than what's out there. So yeah, I think this is kind of cool. And what's the future of all of this? EPROP only works for a single layer. So the first thing we want to do is to generalize it to multiple layers, right? So that's something that we intend to do. We also intend to integrate it into our own environment that we have. We have this like other package that's called Snacks. So we aim to implement these together so that you have like a much nicer and streamlined user experience. We're also working with Yota Pairazi's group to use this stuff that I just presented to make dendritic neural networks faster. And also me personally, my PhD is pretty much about what I just presented. I also want to like learn these approximations directly from scratch using RL. So this is all the stuff that I work on. Finally, what I also want to do, or what we like to do, is integrate hardware constraints as well, right? Like sometimes you maybe just want to use approximations because certain things are very expensive to compute. So these are things that we are thinking about in the future. So yeah, that's it.